Here we see a potential difference being created by a power supply in order to cause a current to run through these wires, lighting the light bulb. This demonstrates how a current-carrying wire creates a magnetic field. When the wire is brought close to a compass, the compass deflects, and when the wire is brought back away from the compass moves back to where it was before.
Every current-carrying wire creates a magnetic field. To determine the orientation of the magnetic field, we use something called the right-hand rule. Point your thumb in the direction of the current and curl your fingers in the direction of the magnetic field.
In this section, we demonstrate how a battery, a wire loop, and a magnet can create a motor, as seen here. Now, this is very similar to the way that the bike generator works, which we will show you coming up soon. The wire loop spins because there's a difference in the magnetic field caused by the magnet and the magnetic field caused by the flow of current through the wire. Now, I will demonstrate here how I can stop it by adding another magnet on top to balance out the magnetic field. It'll work.
It stopped for that brief second.
And here it has come to a stop now. Now, the reason that it did that was because I brought it too close and created a different imbalance, which made it spin faster the other way. Much like in the motor, how the electric field changing caused the wire loop to rotate, in the bike generator, a rotating wire loop inside of a magnetic field in the motor of the bike generator causes electric current. This is called induction, and it can work both ways. Now, if Tristan gets on the bike and pedals the bike, you should see that these light bulbs will light up due to the induction caused in the motor. And if he stops, they'll turn back off because there is no more changing field, meaning that there is no more current.
Our hypothesis is that as you give the bike greater RPMs, it generates a greater voltage and a greater current, and therefore the board will get more power and the light bulbs will have a greater brightness to them.
For our experiment, we decided to have the independent variable be RPM, which we tested at 0, 60, 90, 120, and 150. We had the dependent variables being current, voltage, and brightness, and we measured those with an ammeter, a voltmeter, and a lux meter, which Josh will now show you.
Alright, so here we have the ammeter, and it is set up in series with the rest of the board, where the input's here, and then this circuit right here controls power to the whole board, and it's in series so that it can measure the current throughout the entire board. Here we have the voltmeter, which is set up in parallel to the board, so we can measure the voltage drop from beginning to the end. And here we have the lux meter, which we use to calculate the brightness of the bulbs as the RPMs are changing.
And we do the brightness, the lux meter, when it is dark so that we can get a more accurate reading. And we take the brightness of only one bulb so that we keep a constant reading between each experiment.